Hi there, welcome to lecture 21 of Machine Learning from Data. We're going to continue talking about neural networks and specifically fitting the data to obtain your final hypothesis G. And in order to do this, we're going to talk about forward propagation and backward propagation, two famous algorithms that are really what brought neural networks back into the limelight in the mid-80s and early 90s. Okay. But we will have to address the issue of are we fitting the data or are we overfitting the data? Okay. So lots to come. Quickly, what did we do last time? Last time we introduced the multi-layer perceptron that demonstrated the awesome power of being able to cascade linear perceptrons. And basically now we can implement any function to within any given accuracy. Okay, so we started with the biological inspiration of neurons in the brain, and in the bottom left we see the engineering device, the neural network at a high level in all its glory, which is what we're going to use. Okay, so this is just to show you that biology gave us the inspiration, but engineering success might require something that looks a little bit different. Okay. And last time we developed a notation for the neural network. Okay, and so if you drill down deep into what's going on at a particular node in your neural network, which is a feed-forward multi-layer neural network, okay, there are inputs to a node which we call SL, and outputs from a node which we call XL. The inputs to the node came after multiplying by weights connecting to the layer L, and the output for the node, is going to get multiplied by weights connecting to the layer L plus 1. Okay? And in this way, you can think of, you initialize the network on the left and with your features, and then those propagate to inputs of the next layer, and then outputs of the next layer, and then inputs of the next layer, and so on. And so the input features propagate all the way to the output final layer and produce your final hypothesis h of x as shown in this picture. Okay, and we summarized this notation. So into a layer are the signals SL. We can collect them into a vector, okay, a DL dimensional vector. The outputs are XL, okay, which is DL plus 1 dimensional vector. The plus 1 is because it's augmented by the 1. Okay, and then the weights into layer L we denoted by the matrix WL. Okay, and the weights out of a layer we denoted by the matrix WL plus 1. Okay, now don't worry, we'll go over these notations again on the board. Specifically, we'll first have to decide, how do we compute the output h of x for the neural network? And in particular, what does it depend on? Well, it clearly depends on, the inputs, which you initialize the network on at the left, so x1, x2 up to x sub d. But then it depends on all the weight matrices. Okay, so all the weights on the edges, and I'm allowed to tune those weights. That's what gives me the awesome power in the neural network. So we will sort of heuristically represent all these weights by the parameter capital W, okay, which has the weights into layer 1, the weights into layer 2, the weights into layer L, okay, the output layer capital L, okay, and all these L weight matrices comprise all the parameters that we get to tune in the neural network. So we can specify, and each of these, weight matrices, W1, W2 up to W big L, are matrices. Okay, so W is a collection of L matrices, and if you specify these L matrices, you have actually specified the network, and implicitly you've also specified the architecture, and we'll see how that works. Okay, and now we get to choose these weight matrices in order to fully specify the hypothesis h of x, and then the question becomes, how do we choose them? We need to fit the data. Okay, so we need to choose them to fit the data, and that's the topic of today. So let's go to the board. I've redrawn the neural network here, and let's go through it, to build some intuition for what's going on. So in the first layer we have our input features, the augmented one, feature 1, feature 2 up to feature d. So this input layer has dimension d, okay, and it has d plus 1 nodes. Okay, now what's going on? So in the next layer we have, in this example, 3 nodes. Okay, and each of these nodes is essentially computing a perceptron on the previous layer. Now it would be a perceptron if this theta was a sign, but we're going to soften the sign and make everything more mathematically convenient by using tan h. It's an approximation to sign. Okay, so theta is going to be tan h. But effectively what's going on is this vertex, this node in layer 1 is computing the red perceptron of the input. This node is computing the green perceptron of the input, and this node is computing the blue perceptron of the input. Okay, so we compute 3 perceptrons on the input, and for each of these perceptrons you have the red weights, the green weights, and the blue weights. And so we store each of these weights as a column in the weight matrix W1. 1 for layer 1. Okay? Now, each of these is computing a perceptron, so they have an output. So this layer has an output vector. Okay? And so what's going on in the next layer? Each of these nodes computes a perceptron, the red perceptron and the green perceptron, for the output vector that's produced by the previous layer. Okay, so you have 2 perceptrons being computed, and the weights for those 2 perceptrons are stored in the weight matrix W2. Okay? And then these perceptrons have output. Together with the augmented one, we compute a final perceptron in the final layer and output h of x. So what does h of x depend on? Well, certainly depends on what you put for the inputs here. Okay, what are the input features? But what else will change h of x is if you change any of the weights. So h of x depends on these weight matrices and and the input data. Okay, now let's drill deeper into a particular node. So I've highlighted a node in layer L, node I. Okay, so this node will have an input, and we will typically call that input SLI. Okay, so there'll be an input to node 1, to node 2, to node I, to node DL. DL is the dimension of layer L. So there'll be DL inputs. I can collect all those inputs in a vector. I call this vector SL. Okay, so what's the dimension of this vector SL? It's exactly DL. There's SL1, SL2, up to SLDL. Okay, so this input vector into the layer now, okay, which is composed of each of the individual inputs to each node in the layer, is a vector of dimension DL. Okay. Then we can compute the output, okay, from this layer. Okay. And each node in this layer, okay, produces an output. So for example, node Li produces the output XLI. Okay. And I can collect all these outputs in a vector XL. Okay, and I put the augmented one. So I have the output vector from this layer, XL, which is 1. Okay, then XL1, the output from node 1, from node 2, from node I, from node DL. Okay, so there's 1 plus DL outputs from the layer. So the output vector XL is 1 plus, has dimension 1 plus DL. Okay, so that's the output vector. Okay, and we're focusing on specific node and a specific layer L. Okay. So let's see, how do we compute the input to this node Li? Well, it's basically the signal. The signal we're basically computing as input signal, which gets transformed by tan H. This input signal is basically a perceptron, the linear signal. Okay. So how do I get this input signal? I have a red perceptron because it's a red. I've colored this node red. So I implement a red perceptron on the previous layer's output. Okay. Now, what's the dimension of the previous layer's output? Well, the previous layer had dimension DL minus 1. Okay, so if you augment it with the 1, then the output vector from this layer has dimension 1 plus DL minus 1. Okay, so that's the dimension of this output XL minus 1. We compute a perceptron, we compute a linear signal, okay, on this output, and this red perceptron, which is one of the columns of weights in WL. So we compute this red perceptron. That's the input to signal to this node Li. Okay. And then we output it and we deal with it in the next layer. Okay. So this perceptron, this red perceptron weights are stored in this weight matrix WL. This weight matrix WL is going to have a perceptron for each node in this layer, because each node is computing a perceptron. Okay. So how many perceptron weights does it need to have? DL. Okay. So if we drill in to this weight matrix WL, it has a set of perceptron weights W1 for layer L, W2 for layer L, it'll have WI for layer L, all the way to WDL for layer L. Okay. So there are DL perceptrons which are stored as columns in the weight matrix WL. So this weight matrix WL has width DL. DL columns. Okay, and what's the dimension of each of these perceptrons? Each of these perceptrons has a dimension which is corresponding to the augmented output from the previous layer. Okay, so the augmented output from the previous layer has dimension 1 plus dimension of layer L minus 1. Okay, so 1 plus DL minus 1. Okay, so this weight matrix is a DL is a 1 plus DL minus 1 by DL dimensional matrix. Okay, so now let's mathematically define how we propagate the feature vector forward in this network until we ultimately get the final output h of x, and this is called the forward propagation algorithm. Okay, so how do we compute h of x? And it's all really embedded in this discussion of what's going on at a node. Okay, so let's come back and we're going to discuss forward propagation. So, forward propagation, or how to compute the output h of x. Forward propagation. Okay, now the reason we have to discuss how to compute the output, okay, because as you can see, this visual representation is sort of, nice, it's convenient, it lets us know what's going on, cascaded perceptrons, okay, but we don't have a very nice, convenient formula for the function h of x, okay, like we did for the linear perceptron. We don't have a convenient formula, okay. In fact, we could construct one, okay, but it would be a very cumbersome, almost useless formula to look at, okay. Instead, okay, we can get a very nice, convenient general algorithm, okay, that takes as input the set of weight matrices, okay, so we will call the set of weight matrices W, okay, so the set of weight matrices, take the set of weight matrices W, okay, and the input, and then this algorithm just runs and produces the output, okay, so it's an algorithmically specified final hypothesis, although if we wanted to for a fixed collection of weights and a fixed input feature, we could sit down and write the explicit function, but it's not much practically useful. It's not really useful. Okay. Now, I'll just mention that, by looking at these weight matrices, so this weight matrix has embedded in it the dimension of this layer and the dimension of this layer. This weight matrix has embedded in it the dimension of this layer and this layer. This weight matrix has embedded in it the dimension of this layer. So if you tell me what the weight matrices are, by just looking at their dimensions, I can reconstruct the network. So implicitly, by specifying the weight matrices, and that's all you need to specify, you have not only specified the architecture of the neural network, but you have also specified what weights go on each edge. And that's typically how we specify the neural network. We say, just give me the weight matrices. You've told me everything I need. Okay. So now, let's focus on, the input to node Li. So the input to node Li is, the ith column of, it's a perceptron, okay, that's being computed with respect to the previous layer's output. Okay, and what are the weights of the perceptron? It's the ith column of L. Okay, so the input to the input SLI is just the perceptron computed using the ith column of the weight matrix and the previous layer's output. So it's just the ith column. So the weight matrix is the ith column of the weights are the ith column of the weight matrix transpose XL minus 1 applied to the output of the previous layer. So this is just the linear signal. So this is the linear signal. Okay, and this here are the weights of perceptron computed by node Li. Okay. So, you can think of this as, a row. So SLI is this transpose, which is a row times the previous output. Okay, so let's now look at the vector SL. Okay, is SL1, SL2, all the way to SL what? What's the dimension of the output? DL. Okay, so let's look at the weight, the entire input to this layer. Okay, the entire input to this layer is just, the weight matrix WL1 transpose, okay, which is now a row, times XL minus 1. WL2 transpose times XL minus 1. WL3 transpose times XL minus 1, and so on up to WLDL transpose times XL minus 1. So this is just the matrix WL transpose. So the signal SL, so summary, okay, the signal SL is equal to WL transpose XL minus 1. Okay, so we can compute that entire vector signal into the layer L with just one matrix multiplication. So the matrix multiplication of the weights WL, okay, transpose times the vector output from layer L minus 1. This matrix representation is very useful when we come to implement huge networks, okay, in practice, okay, because we can specialize hardware and architectures and algorithms that can become specialized for computing this matrix vector product. Okay, and you can distribute it on GPUs and so on and so forth. In fact, GPUs have become very good at computing matrix vector products. Okay, so if you want to speed up, the computation of this signal, you just speed up the computation of a matrix vector product. Okay, so let me erase, what led up to the signal. Okay, and now that we have the signal, we can compute the output. XL is just, and I'll heuristically write it as theta because they're all using the same transform. So I apply this transform theta, tan H, I apply this transform theta to the signal, okay, and add the augmented one. 1 theta of SL. Okay, so mathematically, that's what's going on in layer L. Okay, now let's put this together. Let's cascade and get the final output H of X. And that's the forward propagation algorithm. So the algorithm, okay, so forward propagation algorithm in step 1 is to initialize. So let me just tell you what we are computing. Okay. Given the weights, WL, okay, W1, 1, W2, and so on, up to WL. So you're given the weights, okay, and you're given an input. So these are the weights, the architecture and the weights of the network. So the weights, and the input, X, which is 1, X1, X2, up to XD. Let me call it little x. Okay, so this is the input. Okay, compute H of X. Okay, and it's a straightforward, very simple dynamic programming algorithm. You compute the output of the 0th layer. So step 1, initialize. Okay. Compute the output of the 0th layer. So X0 is just initialized to X, the input features. Okay. Now propagate the output of layer 0 to the output of layer 1, then to the output of layer 2, 3, 4, and finally to the output of layer L, and then you're done. Okay, so this is initialize. Step 2, propagate. Propagate. Okay, so assume, okay, so in some sense, compute, so set, the layer that you're working on, L equals to 0. So you've initialized, layer 0. Okay, now propagate. Set L equals to L plus 1. So we're going to now compute the output of the next layer. We started with L equals 0. Okay, and we compute first the input to that layer. Okay, SL is equal to WL. We have WL, it's one of the inputs. Transpose X L minus 1. Okay. So when L equals 1, we use X0, which we have computed. And once we have computed S1, okay, we need X0, which we have. And then we compute XL. The output is just, 1 theta of SL. Okay. So you propagate, okay, until you have X big L, okay, and X big L, H of X is just X big L. Okay, so this is the 0th, this is X big L, so this is the 0th component, the augmented one. Okay, so there's the augmented one, and then there's the output X big L, 1 of the first non-trivial node, not the augmented node, the first non-trivial node. Okay, so you just initialize and propagate. Okay, we could say, you start at L equals 0. Now for L equals 1 to big L, okay, you output in this way. set L equals. So effectively what we're doing is for L equals 1 up to big L. Okay, and then when we have XL, output XL, the first output. And it's very easy to update this if you want more than one output. Okay. So let's say you're doing a massive vision problem and you have 25 classes, apple, orange, dog, cat, and so on. So then you'll have 25 outputs and you can view the output H for each of these outputs as the probability that it is that class. Okay, I'm not going to get into those details. We're going to focus on the basics. Okay, so that's forward propagation, or how do we compute h of x? Okay. At a high level, what's going on? Okay, so let's just show you what's going on in forward propagation at a very high level. So at a high level, you initialize your neural network with x, okay, and then the first layer weights, x, which is x0, which is initialized to the layer 0 outputs, and then your first layer weights come and give you the signal that's going into the first layer, and then you transform and you get the output of the first layer, okay, and then you apply the weights in the second layer, okay, and you get the signal into the second layer, and then you transform and you get the output of the second layer, okay, and eventually you get the input to the nth layer, you transform and you get the output of the nth layer, okay, and that is h of x. Okay, so now when you have your data, you have x1, x2, x3 up to xn, and y1, y2, y3 up to yn. Okay, so you can send each data point through your neural network, and you can get h of x1, h of x2, h of xn. Okay, and now you've computed the output of your neural network for each input. And what do I need to compute these outputs? I need the weights. So I'm assuming that the weights are given. Okay, so for given weights, W1, W2 up to WL, okay, we can certainly compute the output, okay, which means that we can compute the in-sample error, En of H, which is specified by the weights, is equal to 1 over n, and let me illustrate with the squared error. Sum from sum from little n equals 1 to big N of h of x little n minus the y value, y little n squared. So this is if we're doing, let's say, regression and we're trying to minimize the squared error. If we were doing classification or logistic regression, we would have different errors. Okay. Actually, classification error is also a squared error, but if we were doing logistic regression, this would be the cross entropy error. So we can, in general, write the in-sample error as the sum 1 over n, the sum over n equals 1 to big N of some error function which takes as it which is computed for h of xn and yn. Okay. And okay, what's the goal now? So this is just saying that if you give me the weights, I can compute my hypothesis outputs for all of my data, and I can compute the in-sample error. Okay, that's nice, but that's not the main work that we need to do when we're performing learning. We need to learn. We need to fit these weights now to the data. So in other words, we need to find the weights, okay, that minimize the in-sample error. So we need to fit the neural network, okay, neural network NN to data, i.e. find the weights that minimize the in-sample error. Now, whether or not that's a good thing to do, we'll deal with that later. That's the issue of overfitting. But for the moment, okay, we need to at least be able to fit the data. We need to find the best looking weights. Okay, and one of the reasons why we put the tan H here is because it's differentiable. We cannot the perceptron on it was already a tough optimization problem. We cannot analytically find these weights, okay? So we need to numerically find these weights, and so we're going to use gradient descent. The algorithm we saw before, this iterative algorithm to minimize a function, okay, which we saw before in the context of logistic regression. Okay? And so the idea here Imagine that, we have the weights, okay? The idea here is to figure out what's the gradient of the in-sample error with respect to your weights, okay? And move and do gradient descent, so take steps in the direction of the negative gradient. So, we're going to update WL, gets updated to WL plus minus your learning rate times the gradient, okay, so the derivative of the in-sample error with respect to your weights WL. So imagine that I want to move let's say I want to move the weight matrices, I want to move the weight matrix W in layer L, okay, in order to improve the in-sample error a little bit. So I figure out the gradient of the in-sample error with respect to the weights WL, and I move a little bit in that negative gradient direction. Okay, and what is the gradient of the in-sample error? Okay, so the gradient of the in-sample error with respect to WL is the gradient of a sum. Okay, so it's 1 over n, the gradient of a sum, but that's a sum of gradients, a sum from n equals 1 to big N, okay, of the gradient of E of h of xn, yn, with respect to dWL. Okay. So we see that we need to be able to take the gradient of this error function with respect to the weights WL. What is the gradient? Effectively, the gradient is saying how much does this error function change if I change the weights. The change in the error function divided by the change in the weights. That's effectively what the gradient is, the derivative. Okay. So, summary. We have a way to compute the output. That's nice, which gives us a way to compute the in-sample error. Okay. And, which is good, but, I can compute the in-sample error for a pre-specified set of weights. Okay, so if you pick random weights, I can compute the in-sample error, but that's not what we want to do when we're doing learning. We want to fit the data. Okay, we want to find the good weights, okay, the weights that minimize the in-sample error. Whether that's a good idea or not is yet to be seen. Okay, and in order to find the good weight, we need to be able to compute the change in the in-sample error or the change in the pointwise error with respect to a change in the weights, okay, in order to run gradient descent. Okay, now in practice, people are using massive networks with, 1 million parameters and so on and so forth. Okay, so, we have to, at some point, pay a little bit of, attention to practice and efficiency. And we want things to end in a year or in our lifetime. Okay, so quick exercises for you. Okay, so a quick exercise. So we will now, focus a little bit on efficiency as well. So computing the in-sample error. Okay, so if you have n data points, n data points. Okay. And a neural network architecture specified in this way. So imagine that your dimensions of each layer are D0, which is the input dimension, D1, D2, up to D sub L. Okay. So I'll give you a couple of sort of exercises, okay, quizzes. Okay. How many weights are in this network? So, how many weights? I.e., what is the size, the number of entries in W1 plus, plus W2 plus all the way to plus WL. Okay, let's call the number of weights big W. So let's call this W. Okay, size of W. Okay. How many vertices or how many nodes? Let's call that V. How many nodes? Okay. And in order to compute the in-sample error, how many times do you need to compute or evaluate this function theta to compute E in? How many multiplications? So 1 and 2 computations of theta. Okay, so it's very helpful to sort of sit down and answer those pop quizzes. Okay, and I'm going to erase while you answer those pop quizzes. Okay. Okay, so if you did those little pop quizzes, so here's what you should have found. In order to compute h of x, each weight will multiply a corresponding output from a node. So each weight will be touched once for a multiplication. So number of multiplications is equal to the number of weights or number of parameters in your network. So it's equal to the number of weights equals number of parameters. Okay. And the number of times you need to compute this activation function tan h, theta, so the number of computations of theta computations. So you get the signal into the node, you compute theta, and you pass it out, and that's it. You never need to compute theta for that node again. So it's equal to the number of nodes in your neural network, which is just the sum of the degrees, basically. It's just the sum of the degrees. Okay, and so in order to compute the in-sample error, okay, we have to compute. So this is to compute h of x. We have to compute h of x n times. So compute E in requires, n times the number of weights, multiplications plus n times the number of nodes, computations of theta. So this is multiplications. And this is theta computations. Okay, and so, if the theta computation is very costly, then in practice we might choose another activation function, not the tan h. And that's what is the, one of the rationales behind these various, piecewise linear. So 0 up to some threshold and then increasing linear. Okay, so those are much faster to compute. They basically computed using multiplications. Tan h is a relatively expensive, computation. Okay, now to do gradient descent, we need to be able to compute basically the derivative of the in-sample error with respect to a change in the weights. So if you imagine that you have the weight in layer WL going from the previous node I to the layer L node J, okay, so then the derivative of the in-sample error with respect to this weight is approximately equal to, almost by definition, is approximately equal to the in-sample error, for the weights WL, IJ, plus some tolerance H minus the in-sample error, okay, for the weights WL, IJ minus some tolerance divided by twice the tolerance. Okay, so this is the finite difference approximation to the derivative, to the gradient. Okay, and so we need to compute this. We need to compute this. Compute for all weights. Okay, so this is size of the number of weights. Okay, the size of all the weight matrices added up together. So we need to compute this for all the weights. Okay, and so let's see how long it's going to take us to compute. Well, we need to compute so what does this notation mean? This notation means that I'm computing the in-sample error by perturbing these weights up h, leaving all other weights the same, and perturbing the weights down h, leaving all other weights the same. I compute the change, the sensitivity of the in-sample error, the change divided by h. Okay. So I need to compute this, and this is what's sometimes called the numerical derivative. Okay. And it's an approximation, and you can get it more and more accurate by choosing h very, very small. H approximately 0.0001 will give you a pretty accurate estimate of the gradient. 0.0001. Okay. The error in the estimation is order of h squared. So you can do the Taylor analysis to see that the error is order of h squared. Okay. But you have to compute this for all the weights. You have to compute the derivative to get the gradient. The gradient is the derivative, is the vector of derivatives with respect to all the weights. So you have to compute this derivative with respect to all the weights. So that's W computations. And each of these is taking basically NW. Okay. So this in-sample error, okay, is going to take running time to compute of order of NW, okay, plus NV times W.
where I've kept these separate because this is theta computations and this is multiplication. So, but basically NW squared. And nowadays people want to use neural networks with a million parameters. Okay, and to use a million parameters, you better have a lot of data to train it. So N is going to be also order of a million or more. Okay, so you've got a million squared. That's 10 to the 12 times a million. That's 10 to the 18. Okay, that's 10 to the 18 just to compute one gradient. Okay, and now you have to do gradient descent, so you have to compute the gradient many times. Okay, so the numerical derivative is a very simple way to compute the gradient. Okay, and whenever you compute the gradient, so you can, if you analytically compute the gradient, you can always use the numerical derivative to check your analytical computation, but it's not a very efficient way to get the gradient. Okay, and we would be done with neural networks if we didn't have a more efficient way, not to mention the fact that it is approximate. Okay, so now I'm going to come back and show you a very efficient way to compute the gradient. Okay. Essentially, we can compute the gradient in the same running time that it takes us to compute the in-sample error. Okay, so it's almost as efficient as just computing the in-sample error. Here you see computing a single gradient, a single derivative, is as efficient as computing the in-sample error. We're going to show that computing all these derivatives is as efficient as computing the in-sample error. So we can remove this W. Okay. And it's a dynamic programming algorithm that allows us to compute all the gradients. Okay. It's a little bit sophisticated. So, the first time you see it, you're not going to understand it. The second time you see it, you're not going to understand it. When you come to implement it, that's when you will understand it. Okay. And so we'll go through this famous algorithm. It's a dynamic programming algorithm that allows us to compute all these derivatives in one shot. Okay. Getting rid of this factor of W. Okay. And that algorithm is called backpropagation. So let's erase and come back and talk about this algorithm, backpropagation. It's essentially an algorithm that allows us to get the gradient in an efficient way. Okay, it allows us to get the gradient in an efficient way, and then we just use it in the gradient descent algorithm, okay, to fit the neural network to the data. To implement gradient descent, we need to compute the derivatives with respect to the weights. So we need, the derivative of the error, okay, and we do it point by point with respect to the weights WL. Okay. Now, let me mention that this is a matrix of weights going into layer L. So this is a matrix of derivatives, one for each weight. So this is a matrix of derivatives. Okay, and what are the dimensions of this matrix? Okay, so this matrix is 1 plus dl minus 1 by dl. So it implements this weight matrix has dl perceptrons, and each of those perceptrons is computed on the previous layer's output, which has dimension 1 plus dl minus 1. Okay, so we need the derivatives of this form, of these matrices of derivatives. In particular, we need every matrix of derivative because we need to do gradient descent. So we need to compute the gradient with respect to every weight, i.e. all the weight matrices. Okay, so what we're going to do is derive this famous algorithm called backpropagation. Okay, and this is essentially dynamic programming. Okay, that computes all these matrices of derivatives in one swoop. Okay, and that's what makes it efficient. Now, okay, it's going to be intense. There's going to be a lot of algebra, a lot of calculus, lots of chain rule, and so on and so forth. So, when you might have to, you might not, get it on the first go. You might not get it on the second reading. Okay, and you'll read the text carefully, and you'll follow the notes, and you'll follow the lecture. You'll only really get it when you implement it for the assignment. And then after that, many of you who go on to just use neural networks, will download a package and use it. But if you want to do research, or if you want to manipulate, or if you want to make things faster, and so on and so forth, then you need to know the nuts and bolts. If you want to tailor the neural network, for example, if you want to change the activation function or something like that. Okay, so we need to compute this matrix of derivatives, okay, and it's going to be useful to have in your mind the picture of what's going on in layer L. So if you have layer L, there's an input SL, okay, then you have your transform theta, okay, and that computes the output XL. Okay, and this output, okay, now how did we get this input? So you have your previous layer, which was sending, XL minus 1, okay, and you have your weight matrix, and this is where the weight matrix WL comes in. Okay, it multiplies these weights. The weight matrix multiplies the output. Okay, and so you're computing a bunch of perceptrons as the input signal. Okay, then you transform, you get the output signal, and then you'll have another weight matrix here, WL plus 1 to compute the signal SL plus 1, and so on. Okay, so that's the picture of what's going on when we're running the neural network to compute the output. Okay, and so we want to get the matrix of derivatives of the error with respect to each weight in this layer. So let's see if we can compute at least the derivative with respect to one of the perceptron weights. So, going into node I, so if this is node I, okay, in this layer L, okay, so there'll be a perceptron, there'll be the perceptron that's implemented by WLI. Okay, so that's a column in this weight matrix, one of those perceptrons. So let's see if we can get the derivative of the error with respect to that column of weights. Okay, so dE, derivative of E with respect to the column of weights, a single perceptron in this layer, DLI. Okay. Now, the interesting thing is that this single perceptron only affects the output through node I's input. Okay. So by the chain rule, this is equal to the impact that a change in these weights has on that signal going into node I. So the derivative of the signal going into node I with respect to the weights, okay, times the derivative, the change. So this is how much the signal changes times, the derivative of the error with respect to the signal. Okay, so times how much the signal affects the error. So the change in the signal times the change in the error due to the signal. This is the chain rule. Heuristically, you can think of these two deltas. So if you approximated this with deltas, this is a change in the weight, change in the signal, change in the signal, change in the error. These two deltas, in some sense, cancel. Okay, and you get change in the error divided by the change in the weight. So this is the chain rule. Okay, and now let's see if we can compute this guy. Okay, so this guy here. So what is the signal? SLI is equal to WLI transpose XL minus 1. Okay, so this is the linear signal. Okay, and we're trying to compute the derivative of the signal with respect to the weights. So the derivative is just going to be the coefficient. Now you can sit down and check this. Or take it from me that the derivative of the signal with respect to the weights is just equal to the coefficient XL minus 1. Okay, and this is, these are the weights. This is a column of weights, so this has dimension 1 plus DL minus 1, and so does this, so at least the dimensions agree, and you can work this out for yourself or take it from me. Okay, so I'll erase this, okay, and we've just computed that this guy is XL minus 1, so this is equal to XL minus 1 times dE by dSLI. Okay, good. Okay. But this is just, one column of derivatives in this matrix. So this derivative, the matrix of derivatives, I'm going to have to do this for each column. So I'm going to get XL minus 1 times derivative of E with respect to SL1. Okay, that's one column. Then the next column will be XL minus 1, dE by dSL2, and so on, XL minus 1, dE by dSL, dL. Okay, I have dL columns. Okay, but now I can just factor out the XL minus 1. So this here is equal to XL minus 1 times a row vector, which is the derivative of the error with respect to the first signal, derivative of the error with respect to the second signal, derivative of the error with respect to the dLth signal. Okay, so that's just XL minus 1, okay, times this, so this is a column vector, times this row vector, which is dE by dSL. Okay, so now this is a vector of derivatives, but I have to take the row version of this transpose. Okay, So what have I deduced? That the derivative of the error with respect to a particular weight matrix in layer L, okay, that matrix of derivatives is given by the output of the previous layer times a vector of derivatives with respect to the incoming signals, okay, transpose. And you can check the dimensions of this and the dimension of this, and everything matches. Okay, fantastic. So let me erase this. Okay, and let us define this guy as the sensitivity with respect to the inputs to layer L. Okay, we'll call this delta L. Okay, and so this is XL minus 1 delta L transpose. Okay, the sensitivity with respect to SL, the input to layer L. Okay, so there, I have gotten an expression for this matrix of derivatives in terms of two. So this is a matrix of derivatives, and it's in terms of whatever the output is of layer L minus 1, and we'll have to deal with that later. What is that? Okay, but whatever it is, okay, so that's an important point, that you can only define the sensitivities, okay, once you know what the input is. Okay, so let us assume for the moment that we have an input. Okay, so the sensitivity of the error is the error on some input. So let us assume that we have an input, and we've done the forward propagation, and we've computed all the outputs. Okay. So then this derivative, now if you change the weights, you will change the output, the error, you will change the error by an amount that is the output from layer L minus 1, okay, and a derivative of the error with respect to the inputs to layer L. Okay, so we're going to call this delta L. Okay, the sensitivity for layer L. Okay. Now this we can easily compute for my input X. So let's see if we can compute this sensitivity, because otherwise it doesn't look like I've gained anything. I've taken one derivative and put it in terms of another derivative. Okay? And this picture is going to be useful again. Okay? So we want to compute the derivative of the error with respect to the sensitivity L. So we want to compute the derivative of the error with respect to the sensitivity SL. Okay. Okay, so this derivative of the error, this sensitivity, this derivative of the error with respect to the signal into layer L is a vector of derivatives. Let's see if we can compute one of its components. Okay. So derivative of the error with respect to SL, let's say I, is equal to, now that SLI, the input to node I, only affects the output, the error, through how it affects the output of that node, XLI. So by the chain rule, this is the derivative of the error with respect to XLI times the derivative of XLI with respect to SLI. But XLI is just theta of SLI. So this derivative is just theta prime, the derivative of this transform, okay, theta prime evaluated at SLI. Okay. So this is equal to theta prime of SLI, okay, times the derivative of E with respect to XLI. Okay. And so that's one of the components in here. Now this is a vector of derivatives, so I need to just collect all these guys up for different I and put them in a vector. So I will write that as, so I get all these components. So theta prime evaluated at all these values. So theta prime of SL. So now this is a vector, and I'm doing component-wise multiplication with respect to this vector of derivatives. So the derivative of the error with respect to the vector, output vector XL. Okay? Except that I only need dimensions 1 to DL. I don't need to consider the augmented one because there's no product in here for the augmented one. This is only for, I going from 1 to DL. Okay? So I get, and I'll use the notation O times to indicate, component-wise multiplication of the vector of derivatives dE by dXL. Okay, so let me erase this and write this a little bigger. Okay, so this is dE by dXL. So let's see what this is. So it's saying that, I want the sensitivity, okay, for the input with respect to the input into layer L. It's the derivative of the transform function evaluated on that input, component-wise multiplication with the derivative, the vector of derivatives of the error with respect to the output of that node. And here I only need components 1 to dl. Okay. So let's see if I can compute this guy now. Wow. Okay. So many times we're going to use the chain rule. And that's why I said this is an intense algebraic derivation. So the derivative of E with respect to xl, okay, is equal to, so now let's see. So how does the output depend on xl? Well, it depends on xl through how xl affects each of the inputs to the next layer. Okay, so by the chain rule, now this is the chain rule. There are many inputs here, so I have to sum over the effects that x has on all of these inputs together with the sensitivity of the error with respect to those inputs. So this is the sum over k equals 1, the sum over k equals 1 to d l plus 1. Okay, so those are the number of inputs here. The derivative of the error with respect to each of those inputs, s l plus 1 k, multiplied by the derivative of that input with respect to xl. With respect to xl. Okay. But again, we know that sl plus 1k, so s l plus 1, the kth node in the l plus 1th layer, is equal to w l plus 1 k transpose xl, which can equally well be written xl transpose w l plus 1 k. So the derivative, so this is now, I want to take the derivative, so this is a linear signal. It also depends linearly on x as well as on w. So I want to take the derivative of this linear signal with respect to x. So the derivative of s l plus 1 k with respect to xl, okay, is equal to w l plus 1 k. Okay, so here I end up with, this is equal to the sum from k equals 1 to d l plus 1, w l plus 1 k. This is the kth column of w l plus 1. Okay, that's this term times dE by ds l plus 1 k. When I weight the columns of a matrix by certain coefficients and add, so this is a weighted sum of the columns of w. Okay, so this is just WL plus 1, and you can do the linear algebra, the matrix multiplication to show that. This is WL plus 1k times the vector dE by dsL plus 1. dE by dsL plus 1. Okay, and by definition, this is just the sensitivity in layer L plus 1. So this is equal to WL plus 1, the sensitivity in layer L plus 1. Okay, so let me erase this and summarize. So this is equal to theta prime of SL O times, which is component by component multiplication for vectors. Okay, WL plus 1, the sensitivity, and so this is the sensitivity in layer L. Sensitivity in layer L is equal to, some expression, okay, WL plus 1 times delta L plus 1. Okay, and I need the components 1 to DL, 1 to DL. And so I haven't really doesn't look like I've gotten anywhere, because all I've done is I said I need this sensitivity in order to compute this matrix of derivatives. Okay, and what I have done is I've analyzed, and gotten an expression for this sensitivity and this sophisticated complex expression. Okay, but it turns out that this is progress, because I've gotten this expression, I've gotten this sensitivity in terms of an expression that involves the sensitivity in the next layer. Okay, so this is so conclusion. Let me erase all the derivation. Conclusion. Sensitivity in layer L, i.e. delta L, is related to the sensitivity in layer L plus 1, i.e. delta L plus 1. Okay. So let's continue that logic. The sensitivity in layer L plus 1 will be related to L plus 2. L plus 2 will be related to L plus 3. L plus 3 will be related to L plus 4, and so on up to the final layer delta L. Okay. And so if I can compute the sensitivity in the final layer delta L, so if I can compute delta L, okay, then this equation tells me what delta L minus 1 is. Okay, and I can iterate and get delta L minus 2. And I can iterate and I can get delta L minus 3. In fact, I can keep going all the way up to delta 1. Okay. And in this way, I can compute all the sensitivities delta. Delta 1, delta 2, delta 3, all the way up to delta L. But I have to start at delta L. Okay, so, we've done all this algebra, and at the end of the day, that's the basic conclusion, okay? That I can compute sensitivities in any layer L by starting at big L and going backwards, okay? And why do I care? Because the sensitivity in layer L multiplied by the output of layer L minus 1 gives me my matrix of derivatives with respect to the weights WL. And that's why I care. So let me summarize that. Let me summarize these equations now, and we will come back and develop the backpropagation algorithm for computing the gradients, and then the full algorithm for using gradient descent on the data, and then we'll look at some results. So now we can summarize. Okay. So we want to get this matrix of derivatives. It's equal to xl minus 1 times delta L transpose. And we don't know what this delta L transpose is. We know we can compute the outputs. Okay, we can even compute the signals. Okay, so what is this delta L transpose? Delta L transpose, delta L is equal to theta prime of SL, the derivative of your transform, evaluated at the input to that layer. Okay, now we're going to do element-wise, component-wise multiplication of two vectors, okay, of the weight matrix into layer L plus 1, okay, times delta L plus 1, okay, and we have, we only need components 1 to DL. This is a DL dimensional component by component vector multiplication. That's why I use O times to indicate that. Okay. So let's erase this. And I'll tell you now how we're going to compute all these gradients. Okay, so we're done with the meat, the hard part of the derivation of the backpropagation algorithm. Now, if you're like me, if you're anything like me, you're not going to believe something until you see the derivation or the proof. And in general, I think that's a healthy attitude, to have always seek the derivation, seek the proof. But at the end of the day, we also want to be practical, and we need to implement neural networks. And so what do you need to know at the end of the day? At the end of the day, it's these two equations that are golden. Okay, this is more or less what you need to know to just implement the neural network. And then if you need to sort of change things, okay, then you need to get into the nuts and bolts. Okay, so the gradient of the error with respect to the weight matrices, with respect to the weight matrix in layer L, is given by this expression, the output of layer L minus 1 times the sensitivity for layer L, and this is a matrix product, okay, and so it has to have the correct dimensions. And we have this, you can think of it as a recursion, okay, but it's like a forward recursion. So we have this forward recursion for the sensitivity in layer L as an expression involving the sensitivity in layer L plus 1. Okay, now let's see how we can use these two equations together with what we know to do gradient descent to minimize the in-sample error. Okay. And what I'm going to describe is what I'm going to describe is stochastic gradient descent. So you pick a random data point. So you're at you've got a architecture, you've got a configuration for your neural network, which means you've set the weights, you've set each of the weight matrices, okay? And now you pick a random data point. So stochastic gradient descent, okay? So you pick a random data point, xn. Okay. And now, you can compute the output and the error that we're currently making on this xn. So you run forward propagation. Run forward propagation. Okay. So what does this do? This sets xn equal to the outputs of layer 0. Okay. And there's an augmented one here, so everything is fine. And then, we're using the weight matrix. W1, we compute S1, and then so this is W1, and then using the transform, you transform the signal into layer 1, into the output of layer 1, okay, and then you compute S2, and then the output X2, and so on, until you get to SL, and then the output XL, and then that is H of Xn, and then you can compute E of H of Xn and Yn. Okay, and that's reasonably straightforward. We know how to do the forward propagation. Okay, so that's the first step. Okay, is we can run the forward propagation, and we know how long that takes. Okay, the next step is run back propagation, and that's going to involve these two fundamental equations. Okay, and the idea here is to compute all the gradients. Okay, so run back propagation. Okay, i.e., compute all gradients. Okay, and then let me show you what that entails. In backpropagation, we now need to compute all the gradients, all the matrices of gradients with respect to each matrix of weights WL. Okay. Now, in order to do that, we need the outputs at each layer, and we need the delta L's for each layer. Okay. And in the forward step, you see we've computed all the outputs for each layer. Okay. So we've got half of what we need in order to compute the gradients. And now let's see how we compute the other half. Okay. And we're going to start by computing delta for the final output layer. So delta L. We start with delta L. Okay. And so now let me remind you what delta L is. Okay. Delta L is equal to the derivative of the error with respect to what? With respect to SL. Okay. And now we can do this computation with any error. I'm gonna work with the squared error. So E is equal to XL minus YN squared. So the output minus YN. So when you have a data point, pick a random data point XN YN. Okay. So E is the squared error. So then this derivative dE by dSL is equal to the derivative of XL minus YN squared with respect to SL, okay, which is equal to twice XL minus YN, okay, times the derivative of XL with respect to SL. And we've done this calculation before, so I'm just doing it quickly, which is twice XL minus YN times the derivative of XL with respect to SL, which is theta prime of SL. Now, okay, in the interesting case where we choose the tan H for all of our activation nodes, and this applies here as well as here, the tan H is particularly convenient because the derivative of tan H is 1 minus tan H squared. So this is 1 minus tan H squared of SL. Okay, but tan H of SL is just XL, so this is 1 minus XL squared. So at the end of the day, we get for the squared error and the tan H activation function, we get twice XL minus YN, 1 minus XL, that quantity squared. Okay, and so this, last step is for the tan H activation function, and this step is for the squared error, but you could implement this entire chain for any error you choose as long as it's differentiable, and for any activation function you choose as long as it's differentiable. Okay, so we have computed delta L. Okay, so this is equal to twice xl minus yn, 1 minus xl, that quantity squared. Okay, we have computed delta L, at which point we can spit out the gradient with respect to the Lth layer weights. So at which point we can spit out dE by dW big L is equal to x L minus 1, okay, which we have. Okay, we've computed all the x's, so x L minus 1 times delta L. Okay, we can spit out that gradient. Okay, good. So let me erase this little derivation and illustrate pictorially what's going on. So for the final layer, we have computed, so layer L, we have computed delta L, and I'm going to illustrate it going backwards. Okay, so we have computed delta L, and you'll see why I have illustrated going backwards, because we're going to start with delta L and then move backwards. Okay, so now we need to compute delta L minus 1. How do we compute delta L minus 1? Well, this is where this equation becomes so handy. Okay, we just take theta prime of S L minus 1. So theta prime of S L minus 1. Okay, O times W L, okay, delta L plus 1, which is, in this case, delta L. Okay, but here we only need 1 up to D L minus 1. So it's a little bit cramped, okay, but essentially I'm implementing this formula, okay, in order to compute delta L minus 1 from delta L. So this gives me delta L minus 1. Okay. And why do I know I can do this? Well, because in the forward step, I have computed the input to layer L minus 1. Okay. In the forward step, I computed the input to layer L minus 1. Okay. And the weights are certainly known. And I have just computed delta L. Okay. So this step is well defined. And the moment I compute delta L minus 1, boom, I can spit out dE by dW L minus 1, the weights going into layer L minus 1, which is just equal to x L minus 2 times delta L minus 1. Oh, sorry, I forgot the transpose. Okay, so now look, I've computed 2 sets of gradients. Okay, let me show you pictorially what's going on. Pictorially, look at what happened. I have my delta L. I multiplied by the weights WL. So I have my WL. Okay, WL. Okay, so I got the result. Multiplied by the weights WL, got the result. Okay, and then for each, component-wise, I multiplied the result of each component by the corresponding component of this vector, which is theta prime of SL minus 1. So I multiply by theta prime of SL minus 1. Okay, and then that gives me delta L minus 1. Look at that beautiful picture. Okay, to show you what's going on here. Let me just do one more step. Okay, one more step is, I can get delta L minus 2. How do I get that? It's theta prime of S L minus 2 O times W L minus 1 times delta L minus 1, but I only need the components 1 to D L minus 2, okay? And at the moment I calculate delta L minus 2, I can spit out dE by dW L minus 2, which is equal to x L minus 3 times delta L minus 2 transpose. Okay, and let me show you pictorially what's going on here. You take my delta L minus 1, you multiply by the weight matrix WL minus 1, Okay, take my delta L minus 1, multiply by the weight matrix W L minus 1. Now I'll send it into each node, so that gives me the signal going into each node, multiply by theta prime of S L minus 1. Okay, and then out pops delta L minus 2. Wow, beautiful. Okay, and in this way I can compute delta L minus 3, spit out dE by dW L minus 3, okay, using the same formula, okay, and so on, all the way to delta 1, and spit out dE by dW1, which is equal to x0. What is x0? x0 is just the input features times delta 1 transpose. Okay, and if I continue this, okay, up until, delta 1, okay, that's the pictorial illustration of this process. Beautiful. And in this process, look what's happened. I've spit out all the gradients of the weights, or all the gradients of the error on this data point with respect to each weight matrix. Okay? And this pictorial is quite, intuitive and quite nice for visualizing what's going on. Essentially, we are running the neural network in backwards. Okay? When we did forward propagation, we initialized with x, okay, the features xn, and then we propagated forward and got x1, x2, x3, x4, x5 up to xl. Okay, and in backward propagation, we're running the network essentially backwards. We initialize with delta L, okay, and then we run it through the weights. Okay, it's a different kind of transform, but it's a transform. We run it through the weights, transform, run it through the weights, transform, run it through the weights, transform, and so on all the way back. So we're running the network in reverse. Fantastic. Okay, and in the process, we ran one forward propagation, okay, and one backward propagation to compute all the deltas, okay. And you see that this backward propagation to compute all the deltas is, again, just like the forward propagation. It's going to touch all the weights once, and it's going to go through each node once, except that here we are computing a derivative of the activation function. So when you pick your transform function, it's important that the transform function is itself efficient for the forward propagation, and the derivative is also efficient for the backward propagation. Okay, but essentially the same runtime for backward propagation, and spitting out the matrix of derivatives is just one matrix multiplication, which is exactly the size of the output, okay, which is the number of weights. Okay. So very efficient runtime, essentially equivalent to 2 or 3 forward propagations. The third one comes from the fact that you have to do these matrix multiplications, and we get the gradient of the error with respect to all the weight matrices. And now in the SGD framework, what do? We update each weight matrix. WL gets updated to WL minus eta times the gradient of this error with respect to its weight matrix. And so you pick a random point, run a forward, run a backward, get all the gradients, update all the weights. Pick a data point randomly, run a forward, run a backward, get all the gradients, do an update. Boom, 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 boom. That's stochastic gradient descent. Wonderful. Now, if instead of stochastic gradient descent, you wanted to do the batch version, the full gradient descent, well, in that case, you need to first, for each data point, do the forward and backward and compute the gradients, and then store the sum of these gradients, because the gradient of the sum of these errors is the sum of the gradients. So you store the sum of the gradients, and then do one update once you've processed all data points once. Okay, and we already saw the pros and cons between the batch version versus the stochastic gradient version. It turns out that the SGD version is what is popular in practice today for 2 reasons. 1, we saw the efficiencies, and 2, because it's much easier to distribute on parallel architectures, especially when your data is distributed. Wow, fantastic. Bam, 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 bam. Okay, so now we have the mechanism for minimizing the in-sample error to choose the weights that optimize minimize the in-sample error. And so that's what it means to fit the neural network to data. So let me show you what happens when we do it on the digits data. Why not? Okay, so we're going to fit a neural network to the digits data, and what I'm showing there on the top right is the small neural network that we're going to fit. That's by no means a deep network, okay? And now we're going to use the intensity symmetry features, so we've got 2 inputs, intensity and symmetry, and then of course the augmented one. So you see the input layer in blue has 3 nodes. The first node is the augmented one, and then there's one hidden layer, so there's just one hidden layer in red. okay? And there are 10 hidden nodes, so there are 10 nodes in the hidden layer. So that hidden layer computes 10 perceptrons, but there are actually 11 red nodes because the first one is the augmented one. Okay, so we have the augmented one and then 10 perceptron, and then the final layer is computing 1 perceptron of those, okay? And then we fit this to the digits data, okay? And look at what happens. Look at the awesome power of being able to cascade perceptrons. And this is nothing. This is nothing compared to the neural networks that people want to use in practice. Okay? So that kind of awesome power is what cascading allows us. Okay? And you look at the picture on the left, which shows how it has fit the digits data. Well, now we are experts. No one needs to tell us. Overfitting galore. Okay, so we need to do something about that. So now we have too much power. Remember when I gave you the nonlinear transform, I said it's like an 18-wheeler and it's going to be hard to break it and stop it from overfitting. Well, this guy is, an order of magnitude worse. Okay, so we're going to have to deal with this overfitting. But on the right, I'm just showing you the comparison between, gradient descent, so the batch version of gradient descent, and the stochastic version of gradient descent, which is sort of what I focused on in the lecture, okay, where we compute for each data point the gradient of the derivative with respect to all the weights, and then update the weights, and then continue randomly picking data points. Okay, so that's the stochastic gradient descent. And the batch gradient descent is also doing the right thing. It's dropping, but just much more slowly. Okay. The other thing to observe, of course, is that the stochastic gradient descent, so what we're plotting is the full error, the in-sample error. And the stochastic gradient descent tries to minimize a little bit the error on a particular data point. So when you minimize the error on a particular data point, the error on the full data, oscillates. It doesn't necessarily go up. And that's what's that jiggly behavior. But on the whole, stochastic gradient descent looks very fast. Okay. So it shows you a couple of things. First, the awesome power of the cascaded perceptrons, the neural network. Even that small, shallow neural network can do wild things on this, digits data with just 2 inputs. Okay. The second is that how we choose to minimize the in-sample error, the optimization method we use, okay, does play a role, especially when we're talking about big data and big networks with lots of parameters. Okay. So in the next lecture, we will address both of these issues. We'll talk about the generalization issue, the overfitting issue, and we'll also talk a little bit about, improved, better methods for minimizing the in-sample error. Until then, checking out!